Let's look at how to derive a rate equation using collision theory and how we can reconcile that with our usual method for determining rate equations. We'll also get some insight into what the constant factors in a rate equation really mean. So here we'll look at a simple two-body reaction of A and B. As A moves through a gas volume, it will have what we call a collision cylinder. This is essentially an area in which any particle B which falls in this cylinder as A moves through the body will collide with A. So how does this work? If we look at a cross section and put A in the middle, the farthest the B can be away while still colliding with A is the sum of their radii. R1 and R2. So now we can define what we're going to call sigma, our collision cross-section area. So sigma is using simply our area for a circle on this collision cylinder, pi d, where d is equal to the sum of the radii 1 and a radii 2. Sorry, pi d squared. Okay, so now we can look at a collision volume. So we have our collision area here as sigma. So what is going to be the volume which this cylinder creates in time? The volume, of course, will be the area times the velocity of the particle times time. So this velocity time function is obviously the distance it's going to travel, which is essentially this line here, which we can call d. So what we're doing here is the distance travelled times the area of the cylinder face. So quite simple there. Now we can look at the number of collisions that a particle of A is going to have with particles of B as it travels through this collision volume. So we'll call this C1 collisions, and it is equal to the collision volume, where v is our relative velocity. Now, relative velocity is different to absolute velocity of each of the particles, and we can cover this more in a specific gases video. However, at this time, we'll just take this as read. And what we times this by is nb over v and time. So what we've done here is we've taken our concentration of B atoms or molecules, and we've times it by our collision volume to get the number of collisions of A with B. Now if we want to get the collision rate, which we can call C2, rate, we'll call this absolute. If we simply differentiate this total number of collisions function above with respect to time, then we get this collision rate function below, which doesn't have the time function as it's differentiated out and will have units of seconds to the -1 as expected. So this is our collision rate. So per second, how many collisions is this atom of A going to have with molecules or atoms of B? So now what we can do is work out a collision density total. So at the moment we've considered one atom of A. However, of course, there's going to be many. So we need to factor in all of the atoms of A now. So for each atom of A, we have this collision rate. So to find out the collision density, we simply multiply the collision rate by the concentration of atoms of A. So this gives us Na, Nb over V sigma Vrel. And this has units of collisions per meter cubed per second. So a density function. This collision density we've derived here is in terms of absolute number of molecular collisions per meter cubed per second. If we want to get this down into a molar formula, then we have to do a little bit of manipulation. So let's first remove Avogadro's constant from each of these number of A molecules and number of B molecules as follows. So 3 den is equal to n Avogadros squared times small n A, number of moles over V, small n B, number of moles of B over V, sigma VREL. What we can do now is divide by NAV, which has units of moles to -1. So we basically remove one of the NAVs, so we just have one remaining. And also, if you may notice, Na over V is equal to the concentration of A. So we can put that in to simplify the equation further. And now we have an equation with units of moles per meter cubed per second. This can be further made into standard units by changing between meters cubed and decimeters cubed, simply by adding a multiplication factor, which I won't show here. As you may remember from earlier rate courses you might have studied, the Arrhenius equation defines the rate constant K as equal to a constant A times e to the minus Ea over RT. This factor, Ea over RT, is a Boltzmann factor, which essentially is saying that the activation energy on the top here and the average thermal energy of the molecules is on the bottom. So this factor determines the fraction of collisions which will have sufficient activation energy in order to actually have a successful collision. As I mentioned earlier as well, there is another factor which is the orientation, but we'll come back to that in a second. So let's define our rate as follows, our reaction rate now as being equal to E minus Ea over RT times by C3 density, which is our collision frequency per volume. And now we have essentially our rate equation. So we will define as follows. We'll take the variable concentrations out the front, and then n Avogadro sigma VREL times e to the minus Ea over RT. So at constant temperature, this equation can be simplified as follows. To take these terms in their entirety as constants, noting that the Ea over RT will be constant at constant temperature, as will VREL, as it also has a temperature dependency. So if we simplify this, we have K times A concentration times B concentration, which is exactly what we would expect for a simple reaction of A plus 1A plus 1B reacting to form substance C. It's going to be first order with respect to each of the reactants. So that's how we derive our rate equation from the collision theory. It is quite crude, and for example, what we've derived as our K constant here often won't, or almost never will, align with experimental results. We have neglected quite a few factors, one being the orientation, which can be fudged in by defining sigma star instead and making this rho times sigma, where rho is a factor which essentially diminishes the number of successful collisions based on the fact that not all collisions, even with the sufficient activation energy, will have the correct orientation to react. And this can bring this aligned with the experimental results. In later university courses, you will see how you can define reaction constants in terms of quantum mechanical properties of the constituent molecules which are reacting their different modes in both translational, vibrational, and rotational. However, as an introduction course, we won't cover that here. So I will go on in future videos to talk more about rate equations and go into some complex examples, including chain reactions and enzyme reactions. So if that's something you're interested in, look on the channel for videos on that. I hope this has helped clear up how we can go from a collision theory of gases to deriving a chemical rate equation.